Once again, very good morning and welcome to SoftTech Asia 2016. Now into its 9th consecutive year, SoftTech has grown to be the premier software testing event in the Asian region. And this year's theme is ROI of testing, and the conference will cover technical, management and business aspects of software testing. And this year, we are introducing the My Open IoT track, which should be something quite in the news and talked about a lot, which is focused on the Internet of Things, and with an emphasis on the testing aspects of implementation of IoT. Ladies and gentlemen, we begin the first session with the first keynote of the day on history and prospective future of test automation. In a moment, I am happy to invite our esteemed speaker. She is Professor Dr. Ina Schiefer-Decker to deliver the first keynote of the conference. Dr. Schiefer-Decker is a director and member of the executive board of the Fraunhofer Institute for Open Communication Systems, Focus, Germany. She's also the president of the Association for Software Quality and Further Education and a member of the National Academy of Science and Engineering. Everyone calls her, she told me, Prof. Ina. Please put your hands together for Professor Dr. Ina Schiefer-Decker.
Good morning, everyone. Good morning. I'm very honored to be here and to speak with you, to you, and give the opening keynote. I'm asked to talk about the history and prospective future of test automation. Before, I wonder, who of you would call him or herself a software tester? Oh, okay, we need to work on that, of course. And I also wondered, well, now I guess it's even less hands up. I wondered who of you wrote some of the original papers on software testing. And original papers, I say, back in 1950s. Okay, that is already a recommendation I can give to you. There are many bright people, and they lived also before, and we stand on their shoulders, and it's always very interesting to see what they come up with before. But to start with, let's talk about software outages, how costly and dangerous they are. For a long time, the most costly outage that was known is the Ariane 5 rocket, which just exploded, and it was over $370 million loss, just because of one single line in the software. Of course, there's a lot more to say about that, but it was pinpointed to some integer computation which went wrong. Already before that, people died due to software outages. There are radiotherapies, and at least 3 people died back in 85 to 87. And this list is ongoing. Of course, you can only pick some of those. Here, Virgin Blue had just a 2 to 3 hours outage, which costed $20 million. Or 2012, that was a week's outage, over $400 million. Okay? And it goes on and on and on. And a lot of those we even do not see because they are not reported to the public. There is a recent study from January this year that just in North America there's over 700 billion losses a year for ICT outages. And that doesn't count only the system outages, but all their implications. so that people cannot work, cannot, so to say, develop further things, revenues are lost, and there's of course just the concrete costs related to fixing the outages. Okay, and that's only North America per year, so that's huge. Well, some other views now from Germany. I don't ask you to read all those German lines. There is the Association of Computer Science, GI. There's a recent initiative in Germany on software engineering. There is, of course, the German Testing Board, and last but not least, this Association for Software Quality. And to start with, the research organization in Germany presents 5 grand challenges in software engineering, and 3 of them are related to software quality. 3. This new initiative pronounces loudly that also Germany needs to further develop software engineering expertise. We are very strong in manufacturing and industrial automation, but software engineering needs to be improved. German Testing Board had a recent survey, and it also popped up that further software testing research is needed. And last but not least, also today we're going to talk about the Internet of Things, which comes again with new challenges along which we need to further improve the methods and technologies. Okay, so what is the status of software quality? Well, it has evolved since decades now. The most recent reference is the ISO standard 25010 on software quality, which brings forward 7 categories where you need to look at. That includes portability, maintainability, security, reliability, it's 8, sorry, functional suitability, performance efficiency, compatibility, and usability. So interesting to see that compatibility, also I would call it interoperability, so to say, pops up to be one of the main categories, like usability, security, or reliability. So it's really about trustworthy systems at the end. Okay, why it's important from another perspective, there are the, I think, annual World Quality Reports by Capgemini and others. They ask around 1,500 CIOs or IT and testing leaders from 32 countries. And their management objectives with respect to quality assurance and IT testing, just top is to protect the corporate image. Second then is to increase the quality awareness. Third is to ensure end-user satisfaction. So these are very principal objectives. Not only then comes increase the quality of software, because of course at the end software is just a mean to do things, yeah. And they are not top. Top are the users, the customers, and what we provide to them. Also, it's interesting to see that now the majority of people say that they will use 11% to 25% of their budget for software testing. And even quite some, almost, well, over 25%, speaks about 26 to 40%. Yeah, and that are also, well, the numbers which you can see in research reports that, so to say, design and quality assurance testing is a kind of the same share in addition to the code development and implementation. Okay. And one even more interesting short is that most of them agree that the efforts on software quality gonna increase. in particular on software testing, within the next 12 months. So almost 60% talk about a growth in that. And only, well, less than 10% see a slight decrease. Good. Now back to the history. Whenever I talk about software testing, I say, well, it is also about test automation, or it is all about test automation, because there are so many things we do over and over again. So there is a fundamental test process along all the things we do in testing. There are comparable concepts, there are comparable methods. So first we need to understand the processes involved in testing. Then if you understand, then you can sort of say, try to see what are the underlying algorithms. And once you have the algorithms, then you can get back, sort of say, specify more precisely the methods, and then bring all together into technologies which combine a set of concepts and methods so that the people at end can concentrate on the interesting things like the test design, and automation then helps to come from a test design down to the test execution and test evaluation. Okay, so the first software bug is told to be a real bug. It was Madame Murray, which sort of say found one in a relay system back in 1945. There is a logbook, and she wrote down first actual case of bug being found. Well, of course, that was easy to fix. Afterwards, it worked again, but well, you hardly would call that today a software bug, of course. But that may sort of say be the story behind the thing that we call the defects in a software bug. I'm not sure about that, but many people tell this story. So, back in 1955, Mr. Bennington wrote already a paper on the production of large computer programs. It was in the proceedings of a symposium on advanced computer programs for digital computers. And this was adapted from a previous presentation he gave. And along that, you see, for example, that they talk already about operational plans, software and systems in operation. They talk about machine specifications, so the target environment. They talk about the program specification, so what the program should do, about a coding specification, so more abstract down to more concrete specification, down to the coding, and then it gets on to the testing specification, the real testing, also along a shakedown, down to the system evaluation itself. Well, nowadays we use a kind of different words, but basically this is already the line of thinking we have. So a software-based system is a part of the reality where we need to agree on the boundaries to the environment. That is where the system should operate in. Then we do specify and try to capture what the system should do. And along the design steps, we come from rather general business-oriented specifications down to technical specifications, how a software-based system is being realized in software and hardware. And then along the lines, we do specify on system level, on component level, how we evaluate the system and assess its functionality, security, performance in the target environments. Okay, that's one interesting thing. And the other that he already said, we find that large programs can now be produced. Unfortunately, they are difficult to test and document. So also testing is here seen in the context of documentation. And there are some further insights. So he talks about stepwise integration testing, so that one by one the components are glued together and evolved over, or analyzed over and over again. He talks about the system test to be near the target environment because there's a real truth if the software-based system would work. He talks about acceptance test as a final step of testing, so from the perspective of the users to see if the system works or not. He also already highlights the fact that software always needs to be seen as part of the final system. Yeah? So it's not a thing in its own, but it's just the mean to make a system more functional, more valuable. And back then, they had already a kind of 38% of test efforts without even counting the system tests. So that's impressive, and I think we really still need to improve the test efforts in daily life. And he pinpoints the fact that testing is just sampling because we never can, both theoretically to the majority of systems and practically to the complexity of the system, test them exhaustively. So it's always about sampling, and the question is, what are good samples and when to stop sampling in testing? Okay, and last but not least, the last citation from this paper, he says that many sad experiences have shown that the program testing effort is seldom adequate. And at that point in time, you start wondering, what did we do in the past to improve this situation, which was, so to say, coined in 1956. Okay, well, there is, of course, a lot of developments along that. Joris Merz collected these insights. Already Alan Turing started to think about the question how to verify and validate programs back in 1949. Mr. Feinbaum talked about the total quality control, which takes into account software system processes, everything in operation. Baker, so to say, said that debugging is something different to testing. Testing is a discipline in itself. There was a first explicit test team created by Weinberg, and then it starts with realizing that we do need quite a disciplined approach to software testing. And then the NATO workshop claimed the software quality assurance to be a major task for the software experts. Going on, then Dijkstra came up from the mathematical perspective with the sentence, testing shows the presence but not the absence of bugs, which many turned into the statement that testing is just about finding bugs, which is wrong, I think. Testing is about assuring quality levels. And along that, you're also going to find bugs. But it's not the only objective to find bugs. Okay, that's very important. A kind of the testers are the ones which give the ready to go for a software-based system. So of course, at the end, the project leaders and managers decide. But technically, the testers say if a software or software-based system is ready to be deployed. Okay, and then there comes the period of many new algorithms like mutation testing, like a collection of test methods, how to select test data, how to analyze the properties of software and test software, like the cyclomatic complexity, and what about software reliability. So not only looking at functional aspects, but also seeing the software in their, so to say, impact on the system and processes they drive. So software needs to be reliable. That was stated back in 76. Well, then we have the process consideration and the explicit stored of businesses on software quality. So the cost of change curve by Boehm, which says the sooner you detect a defect, the better is, the lower the costs are related to that defect. Then SQS was founded in Germany. That is an interesting, sort of say, line here, because it's a German company. It made it to the stock exchange market, but it was really one of the first that made just businesses along software quality and software testing, a very successful one. Then we have first standards popping up, like the A29 by IEEE on how to document testing processes. An explicit research institute has been founded at Carnegie Mellon, the Software Engineering Institute, which I guess most of you know already. Rook published the first V model, which is an explicit process development model, which sort of say interconnects the software design and development with the testing design and development. Then there are new attempts to better intervene testing with the development by promoting the test first principle. And now we are already in the, 80s. So reliability continues. There are special interest groups, for example, in UK on software testing. We have the software quality standard 9126, that is the predecessor of the 25510, which I showed you before. And there is a first test technology popping up. So that came out of telecommunication. Also interesting to see that this American list of, major milestones in testing has noted that this test technology has been provided, the TTCN, and then there has been one further extension to the V model, which is the W, which says, well, at the end we do have software-based systems and test software systems. So the test device versus the device. And this test device needs to be designed and developed like any other software system, but it, so to say, of course, relates to the software system. Its whole sense is to check if the software-based system would work or not. Okay. Then we have, well, that is, I think, the last slide. So we have the chaos report by the standards group, not provided any longer. There has been a lot of discussion about it, how they surveyed what is, so to say, the base data they're going to use, but they always reported there are just small improvements on the software quality. And then 96, there's a testing maturity model, so how to improve the testing processes. And now I added some more lines because this history wasn't, so to say, extended by him, but I tried to do it later. So there are major updates on the TTCN, the testing and test control notation by ETSI. At OMG, the Object Management Group, we also managed to develop a UML testing profile, which brings testing to all UML-based software development processes. We extended TTCN 3 from doing functional testing to real-time testing for embedded systems, cyber-physical systems, as we need them in IoT, for example. And we extended it also with fuzzing concepts so that security and reliability testing is better supported by the technology. So now we are in a kind of having the concepts, having the algorithms, and bringing them all together in technologies, which then enables tools so that a lot of the things are already provided by the tool environment and execution environments for these test suites, so that it becomes a lot easier to enable test automation for the different systems. Okay, oh, I'm talking. No, I didn't get a sign. So, a short run through what we do in testing. Well, one is structural testing, software-based testing. There's basically the code being analyzed, for example, with a flow graph or data control flow graph or data flow graph. And then you take some coverage criteria, derive test cases, and apply them to the code. In functional testing, one starts from the requirements, not from the code. So one starts from a specification or from a model of the software. From that you generate by various strategies the test cases and the test code, and again apply it to the code. And it's not that clear. Well, in the structural testing, it's not clear how to get the test oracle, so who says is right or wrong. And with the requirements, it's harder to really link the test cases to the implemented software. Then we have model-based testing, which sort of say hires up the abstraction level in test generation and test design. So for the requirements, this takes a system model, which sort of say abstractly say how a system could be realized, and then from the system model it generates the code and the test code. Of course, that has limitations because you have a single model from which you generate the system and the test system, which is not that cool, I think. So the next generation has been really to say, well, these are two different concerns. One is to build the system, the other is to build the test system. So both are to be modeled because they have different purposes, different intents. And then, of course, the system model relates to the test model, and you could already analyze, simulate the test design with the system model and vice versa. And then, so you have a separation of concern, requirements get to the system perspective and the system model and the test perspective, how to assess that the system is right in certain considerations with the test model, and from these models you then can generate code by tool support. And that theoretical helps a lot because you can clearly talk about what is a correct implementation or not. You can talk about the soundness of a test suite. You receive the oracle from the models, and you can also argue about coverage, not only with respect to the code, but with respect to the model and the requirements. And you can make use of model transformations so that this handling of the models is well supported. And of course, there are technologies to support that. For example, at ETSI, European Standards Institute, there's a test description language, TDL, which allows to put down requirements from the tester's perspective. In Australia, there are so-called behavior trees, which allow to have IT-independent definition of the requirements for a system. For the modeling side on the test system, we have the testing profile, for example, and then for the execution, the TTCN3, the testing and test control notation. That means there are standards, there are tools, there are processes in order to apply those things. Okay, last but not least, some future perspective. So, well, this story doesn't stop. Yeah, so I talked about the separation of concern, and more and more people say it's not enough just to separate on modeling level, but we should separate already on testing level. So the informal initial requirements for a system turn to system requirements and test requirements. And as a model-driven engineering is superior to any other manual development method, one uses also models to specify the system requirements and to specify the test requirements. Then we get into the system model, the test model, and the system code and the test code. Yeah, and this is real test automation. Yeah, this is, so to say, how you come from informal initial requirements that we're always going to have down to a systematic, well-documented, well-analyzed process of developing their systems and their test systems. Okay. And, well, so far I only talked about system and test system, but in fact, this is again a set of systems. For example, the SUT system on the test typically consists not only of several components, but consists of several systems again. And then this is to be surrounded by a test environment which consists of real devices which are ready to be used, virtualized devices where you do have the software but not the hardware out of good reasons, for example, because you won't afford all the million smartphones we're going to have. You would use monitors to see the underlying interfaces and their working. You would use real test devices, so special hardware which is able to do precise real-time testing. You would use simulators, which, for example, in a car engine control software would emulate all the physics for the driving. And you would also use virtualized test devices, so where, so to say, the test components run that we typically use in software testing. And we need to master this set of systems. An integration combination of systems from the system and the tester side. That is a lot about configuration, about management, about versioning, about consistency between the views on the system and test system, and so on and so forth. So, I guess you all know the ISTQB and the International Software Testing Qualifications Board, which is supported here by the MSTB, the Malaysian Software Testing Board, which provides a syllabi on how to develop as a software tester professional. It starts with a foundation level, the advanced, then turns to the advanced and the expert level. It has the main line of, so to say, foundation and then test management, technical analyst and technical test analyst was the first, sorry. And there are expert modules on improving test processes or doing test management right. And they are now supplemented with supporting modules on how to do test automation, how to do security, how to have testing within HI development, in automotive, how to do model-based testing, and so on. And this is still quite concentrated on software, so that we created a new initiative to turn, so to say, or extend this perspective into a more system-oriented view, so that we also can talk about embedded systems foundations from the tester's perspective, and then maybe have, so to say, the different versions supported by IoT, because Internet of Things solutions in the industry are different to those in the public space, are different to those in the consumer electronics. But I put question mark behind because this is all ongoing and by far not clear what we do about it here. Okay, now last but not least, I came across some statements from colleagues which were asked 10 years ago about their assessments, what would be. Yeah. They said, so it was 2006, yeah? And they said in 2010, well, we would first have someone in jail because of wrong software. Well, to my best knowledge, this doesn't yet happen. Yeah. And someone else said, well, we will become acquainted with people dying due to software defects. I think that is already the situation now, but it's not, so to say, brought to the attention of the society. Yeah? But we need to be aware of that. We need to do our homework. We need to understand how critical the software-based systems are nowadays. Okay, then 2020. Now that's the prospective future still. Well, Professor Ludewig, well, he's sort of say first-generation software professors in Germany. He said, well, at least now we're gonna have not the engineers from other fields, but original computer science engineers which contribute to develop the software. We know about how liability work, how assurance processes work. And Mario Winter said, well, we're gonna have a worldwide accepted curriculum on software quality engineering, which is not yet the case, I say. Thank you. We do have an internationally accepted software testing curriculum, but not yet on the overall quality assurance processes and quality engineering. Well, then Rudolf von Meyen, that one that created the SQS, said, well, in 2035, software becomes that complex and critical that everyone tries to avoid the software defects beforehand. Yeah? And really invest in trying to avoiding them and seeking the remaining ones. And Bernd Hinde, another guy which also was very active back then, thank you. That, well, there's just self-healing software. The software, so to say, repairs itself. Allianz, which is a big assurer in Germany, would be the market leader in software assurances. So that agrees that there never will be a bug defect or defect-free software. There are gonna be technical limitations on the software, so we do need liabilities, we do need assurances on these. Well, and back then I said they're gonna be the software TÜV. TÜV is an organization in Europe and worldwide which assures the technical systems reliability. They started with elevators. Now they do, and gas engines. Now they do every engine or technical system you can imagine. They are still short in software quality. And I think it takes us quite some more time to enable such assurances on software systems and corresponding certificates. Okay, my conjecture, to make it short, I think we need to further elaborate testing methods, both static and dynamic. It is the by far most important instrument to assure quality. Of course, first you need to construct the quality, but then you need to have the teams, the people, the processes to say a software is ready to go. I think we need to turn it from lab testing to production environment testing. I think we need to integrate the functional software with the testing software. At the end, it could be just become one, so that a software component knows how to test its environment and how to be tested. Along digitized networking, smart cities, Industry 4.0, other things, such software assurances and system test associations are becoming more and more important because we talk about critical infrastructures. At the end, we talk about people's life with the software we are building. Okay, that one I said already. So I think it goes to the self-healing idea of software, but this is ongoing research and we need to improve on that. So thank you very much for your attention. I'm ready now, and well, I wouldn't read, but that comes from the heart. Thank you for listening, and I'm happy to answer questions if you have.